So now we are going to move and for those who haven't really reviewed this introduction to binary classification, I think you should before watching this video on object detection metrics, because it's a continuation based on the principles kind of established there. So in this video we are going to look at closely to what really is the difference between an object detector and the binary classifier. And an object detector effectively is something in addition to a binary classifier. It is a binary classifier and a regressor, because both of them are needed to do object detection. And just to sort of recall what we mean by object detection, we definitely have an image. In the object detection kind of problem, we are given an image. The image has some height and some width, and our job here is to effectively do two things. One is to classify that in this region of the image there is, if you like, a class, for example, person here, and also specify the parameters of the bounding box. Usually the parameters of the bounding box are given by either this pixel coordinates or this and this pixel coordinates, or this actually given by this pixel coordinates, and with some height and width information for the bounding box B. I will be calling B the bounding box, capital B the bounding box from now on. And of course, in order for an object detector to be trained, if the black is the output of the object detector, it needs training data, and the training data are coming in the form of bounding boxes, which we will call the so-called P ground truth. And the whole notion, if you like, of the performance metrics in object detection is some kind of metric we need to derive that we kind of represents to us how closely the bounding box that the detector produces is to the ground truth bounding box. And in general, there are three, I will call it events of interest as we observe the object detector output should be concerned, very similar to what we have been saying in the binary classifier. So this is, I will call it the true positive condition, where we have, if you like, a person that is kind of correctly detected, and this was the ground truth bounding box, and the classifier correctly presented to us the right class. This we will call the true positive event. The I as a subscript will be explained a bit later. Then we may have, and of course this is detection, so it is part of a larger image. The second possibility is that we may have some object that, unfortunately, the classifier misclassified as a different class, and we may have actually potentially multiple of those bounding boxes in all these images present from multiple classes at the same time, but we just here outline the first, just one, to make sure that we are sort of understanding the concept. So here we have ground truth, and the ground truth, obviously there is going to be a ground truth was associated with car, the class car, and then this is obviously is called a false positive, and I will call J. And then of course we have the third possibility, where we have, this is our image, there is, if you like, a class of interest over here, but unfortunately we have not really detected it, and this is what we will be calling a false negative k, small letter k. This is, we will be calling this the bounding box, the predicted bounding box, and as we said, this one is our the ground truth, the GT kind of bounding box. So the metric that we will be using from now on to, I will call it represent the closeness associated with predicted bounding box as related to the ground truth is called intersection over union. So in the intersection over union metric is effectively defined as the ratio of the area, as the name implies, of BP, the predicted intersection BGT, divided by the area of B predicted union BGT. Okay, so if I may actually represent it as two bounding boxes, this will be the ratio, and in fact I may have done in the past, put one in black and the other one to be the, I will call it the ground truth, divided by the union. And if I may say, the intersection definitely of these two bounding boxes on the numerator is this area over here, and sorry, the union is definitely this area over there. And it's not really difficult to see that as these two bounding boxes can come on top of each other in the perfect case that the or completely separated, that the intersection over union could be as small as 0 and as large as 1. And I think at this point it's worth noting that the intersection of a union makes some sense to use it as one of the components of building up, if you like, this object detection metric that we are after, only when we are able to compare bounding boxes of the same class, of the target class. Let's say in this specific case, it makes sense only to consider the true positives when we compare bounding boxes, because it doesn't really make a lot of sense to compare bounding boxes when we have an incorrect classification, and over here we actually have no bounding box to compare. And now that we have actually seen the IOU, I think it's worth considering a couple of cases of interest. Again, in the case where we have definitely detected the right class. So in the case where we have a person and kind of detected the person with some form of significant kind of overlap between the two boxes. And the second case where we have again the person with in the ground truth situation. So here is the person nicely bounded by the ground truth box, but our detector is definitely doing is a bit far away from it. So despite the fact that we can actually label this as a person, these are the two cases of interest here, and I think by defining, if you like, what is actually called the Iou threshold, we are able to actually consider those which have significant overlap, which means that the Iou is above a certain threshold. So I will call this Iou is greater than a threshold, and I will denote it as a small letter t as, if you like, a true positive event. And in the case where I have an Iou less than the threshold, then I will consider this to be a false positive. And typically we are considering as true positive events with that have IOU greater, let's say, either something like 0.75 or 0.5. So these are the values that T typically sort of takes. And now, because we have introduced, if you like, this threshold, effectively now we need to we can take the a training data set and kind of trying to understand what is really going on with respect to an output from the detector. In fact, when I say training data set, I meant to say the test data set that we usually use to gauge the performance of the object detector. So you may recall that in the binary classification introductory video, we have actually seen and defined here the precision, quantity, and entity. And in fact, we definitely have seen and understood the trade-offs using, if you like, this probabilistic kind of diagram here with the probability distributions, the trade-offs between false positives and false negatives. And this is, of course, is reflected in the sort of interplay between recall and precision. Okay, so now that we have seen all that, let's now try to define some terms. So let's assume that I have, if you like, a data set that produced ND, which is the number of detections. When I feed the data I'm observing at the end of the day, a number of bounding boxes. This is the ND. So there are ND detections, and obviously the ND, we can write it, the ND to be as part of the discussion we have seen just a few moments ago in the IOU. We actually can say that here we don't get any detections. So effectively, the number of detections could be either because of true positive events or false positive events. So we can actually write it as ND is equal to NTP plus NFP. And because the metric we're interested in is per class, if you like, metric, and also across classes, but first we need to develop the per class metric, we are going to effectively need to take a class and actually understand what are the number of ground truths that we have for a specific class. As you can see here, for the class person, there is in fact the number of ground truths that we have are the true positives plus the false negatives. So let's write down this equation as well. And we write it as NGT is equal to NTP plus NFM. Okay, and now we are able to go ahead and sort of write down the precision and the recall. So the precision is, and as a reminder, the precision was definitely something that is associated with the true positives divided by true positives plus false positives. But over here, we have to effectively do the write down this equation with the specific counts that we have, because at the end of the day, we're trying to find a kind of a computational technique in order to calculate this kind of metric. So let's write down. So it is basically a summation of all the true positive events, and the true positives, I use the index I. So it is TPI from I is equal to 1 to NTP divided by the, again, same thing, from I is equal to 1 to NTP, TPI, plus the false positives. Well, the false positives are the ND minus NTP. So summation for the false positive, we use the index J, false positive J, from J is equal to 1 to ND minus NTP. Okay, so that is the precision, if you like, equation. Nothing really changes here, just basically we put some what we have observed at the output of this test. And here we have the recall. And the recall definitely is associated with the probability, sorry, the true positives and the false negatives. So now we actually have again the same numerator, so summation, from I is equal to 1 to NTP, TPI divided by, from I is equal to 1 to NTP, TPI plus, now for that we use the K index, is equal to 1 to N F negative, where the NF negative is NGT minus NTP of all the negative events. And now we are done. We have written down all these two relationships that we need to process them and understand how we can move into the direction of calculating this metric. As a side note, we talked a little bit about this threshold T, which is called the Iou threshold, and now we can actually see that how this threshold T can actually enter these formulas of precision recall. This Iou is entering those by determining the populations of effectively NTP and false positives. So now I think it's worthwhile reviewing what we have said about this threshold, Iou threshold T. And we can consider the Iou threshold T as a kind of a signal flow kind of diagram, how it is applied. We have at the input ND number of detections, and we can imagine this being effectively split by a filter whose parameter is small letter t, could be 75%, 50%, and so on. So only IOUs, only detections with IOUs above 75%, let's say, are going to result into true positives, and the rest are going to result into false positives. And the false negatives is unaffected by T, because in the false negative situation, as we have seen, there is absolutely no detection, and therefore there's no point of comparing something we don't have against, if you like, an Iou threshold. So I can actually go and definitely insert this as a parameter in all the true positives and false positives, and for kind of make my equation like this for precision and recall. And now I need to consider in a kind of a second stage another filter, and this filter, what it will actually do is it will take the number of true positives that survived, if you like, this Iou threshold comparison, and it will actually make another comparison. And the second comparison we'll actually make is for those true positives, they will actually ask the questions: is the confidence interval greater than another threshold called tau? So I will call this the confidence threshold. Okay, so the confidence threshold effectively allows the true positives to be filtered further, and only a fraction of those will survive. And as you can see, as the larger, the highest this confidence become. For example, if we have 80% confidence that this class is a person versus something smaller as a threshold, you can understand that a much smaller fraction of detections will survive in this kind of a stage. So definitely the number of true positives that survive over here decreasing function of the threshold tau, and so we can actually put here greater than tau, and in order for us to anything which is effectively less than tau here will actually be classified as negatives. And so although we would expect the positives, either true positives or false positives, to actually have this reduce with respect to higher kind of confidence threshold, we are expecting the negatives, in this case the false negative, to actually have an exactly opposite kind of behavior and actually increase with an increasing threshold. So we can actually go and add the tau parameter here. Effectively, this NTP of t comma tau is not a function, but it is a number of events derived into this kind of branch over here, and correspondingly for the false positives and the false negatives. As we said, false negatives that doesn't have any dependence on t. And now we can write our final precision and recall equations that now actually include everything that we have done up to now. So the final, if you like, expressions are exactly the same as the ones, but instead of having just the numbers that we have gotten at the input of this kind of filtering process, in fact we have numbers that we are going to get at the very end of this filtering process, either because of the Iou threshold or because of the confidence threshold. So the final expressions are very quickly: precision is equal to the summation from I is equal to 1 to n tp of t comma tau tpi of t comma tau, and summation from I is equal to 1 to n tp of t comma tau tpi of t comma tau plus summation of from j is equal to 1, and then we have here nd minus, I will call it, it's actually here, it's not NTP, but it's actually a small letter NTP. So it is NTP of t comma tau fp of j of t comma tau. Okay, so this is the expression for the precision, and then of course we have the corresponding expression and the corresponding expression for the recall is, I'm not sure if it is, obviously it's very evident now what it should be. It's going to be a summation from I is equal to 1 to n tp of t comma tau tpi of t comma tau, this term again plus the corresponding now false negatives, but false negative of k of just t, of just tau, just the confidence threshold for the reasons we explained. This is the corresponding final equation about recall.